Hey guys, thanks for checking in with this short little video on finding an equilibrium constant, kind of some clues on what it means and using it. Topic is equilibrium. It's a very deep topic. It's kind of abstract and it takes quite a while to cover all the bases. Here's a simple one. Hydrogen gas, bromine gas, equilibrium, to and fro, forwards and backwards, with two HBr, hydrogen bromide gaseous molecules. We say the reaction is in equilibrium. We say we have a certain amount of this, we have a certain amount of this, we have a certain amount of this. All three intermingling. Um, Maybe, say, for example, 1,000,000 per second of these molecules come together to go forward to make actually make 2,000,000 of these, wouldn't it? Because there's a 2 there. And if that's true, then maybe um, 1,000,000 per second. And what would that be? That would be, let's see, a million per second. Yeah, that would be 1,000,000 per second this way. That would be 2,000,000 per second go this way to make the same amount of this. So anyways, it might look like there's nothing happening. It looks like the concentrations of this and this and this have equilibrated to a constant rate, stopped changing. But indeed, there are still dynamic processes occurring. And the constant is so important. For a particular temperature, the constant for a particular reaction does not change. It just stays the same when we've reached equilibrium. So the rules of writing this, I won't go over those again, but it's HBr in the top, in the numerator, and Br2 in the denominator, and H2 in the denominator. The square brackets mean molar concentration. That's why I put a C here. Sometimes it's a constant of equilibrium if you'd like, and the 2 right there goes as a power right there, which is a huge no-no in kinetics, but it is the rule when writing equilibrium constant expressions. So there's a 2 there, that goes there. If there was a number here, this Br, say if that was a 3, this Br2 would be raised to the 3rd power. And the thing is, this number doesn't change. It's crazy. Or, since those were all gases, another way to write it looks like this. We say the equilibrium pressure constant is equal to the pressure of HBr squared, the pressure of H2 times the pressure of Br2. So this is in exactly the same format as this one, but instead of using molarity, we use pressure. And the Kc and the Kp in this particular case would actually coincidentally be the same, but that's not always the case by any means. Kp and Kc. Measure pressure, measure molarity. So for example, I happen to know that at a particular temperature for this reaction, it's a large constant. It really kind of wants to go forward. In other words, 38,000 means, in other words, I have about 38,000 times more of this than I do of this. In a way, the numerator is 38,000 times bigger than these. Here's a random example. You could say, well, what if my hydrogen molarity was 0.01 molar? What if my bromine concentration was also 0.01 molar? This times this must still equal 38,000, so I could predict my HBr concentration at such an equilibrium, to be about 1.95, almost 2 molar. So I took this one and this one to the other side. And you can play this game with any concentrations you like, any equilibrium you like, any specific constant you like, and we'll have more practice with this. Let's see. So, yeah. Guess that's all I can say about that. Let's go to another example. Here I have some methane and water vapor in equilibrium with carbon monoxide. Oops, forgot my closed parentheses there. And 3 H2 molecules. It looks like I have 700 torr over here, 500 torr over here, 50 torr here, and 5 torr here. There's no way that needs to be at an equilibrium, but I would rather have to be told that fact in the question. So in an equilibrium mixture of these 4 gases, I have this and this and this and this. If I am indeed told all those numbers, that's easy then, straightforward to calculate the constant. Since I'm measuring pressure, let me go ahead and write the pressure of CO and the pressure of H2 cubed and the pressure of H2O, and the pressure, I guess these are partial pressures, right? In this whole mixture, however big it is, I'd have 4 different gases contributing to the total pressure. Could add those up. Would that be 1255-ish or something like that? Interesting. Well, taking those numbers, again, like I said, if you were told the equilibrium concentrations or the equilibrium partial pressures, you take those values and plug them into the expression called the mass action expression, which is the definition for writing the equilibrium constant. And 50 and 500 and 700 in the bottom. Looks like this constant comes out to be kind of smallish, 0.179. Hey, you know what? This is just a kind of math thing, but it is a big deal in equilibrium. If the numerator is small and the denominator is large, then this constant is smaller than 1. And vice versa. In our first example, we saw number 38,000. If this number is large, that means the numerator is large and or that the denominator is small. And if this is large and that's small, then that kind of hints to me that this equilibrium at this particular temperature favors making quite a bit of this as compared to the reactants. But if the constant is small, like we just saw down here with 0.179, that means this is small and or this is big. And the way to say it is this is small and or this is big. This is big. We have a whole bunch of this. If we are indeed at an equilibrium scenario situation, and you don't always have to be. Sometimes you can just throw gases that will comprise or eventually reach an equilibrium into a container, and they'll have their way with each other and reach what nature likes to call some balanced mixture. And that balanced mixture is always described by this equilibrium constant. So equilibrium constant, given the equilibrium mixture, so if we're told that these have already reached an equilibrium and I've somehow measured this one, I measured this one, and I measured this one, then I put the 1.5, the 1.1, those go in the numerator or the denominator? How do I write those expressions again? Oh yeah, here we go. So I'll say the products in the numerator to the second power, the reactant in the denominator to the third power, and plug the numbers in. So if this really is an equilibrium mixture, then this has to be 1.5, this is 1.1, this is 0.47, and I got 0.11-ish, although I haven't mentioned the temperature. If the temperature warms, many reactions go faster and the constant gets larger, but not necessarily. If it's endothermic, it might be backwards from that. Let's see. Now, this is kind of an important point. This 0.11 always stays the same if the temperature stays the same. Even if the volume were to change or a catalyst were added or something weird, funky, this constant at a specific temperature for this specific reaction should stay the same. So if my numerator got a little bit bigger, then something down here would have to get a little bit bigger as well. So as the ratio would have to still be 0.11. Or if this got a little bit smaller, then this would have to be a little bit smaller, so as to make that still 0.11. Yeah, and that's the nice thing, is you can count on the equilibrium constant being indeed constant for particular temperatures. Not like universally constant, because if the temperature changes, then the conditions change and the constant changes. But short of that, the constant being constant is very useful. Here's another reaction. 2 HCl gas molecules, 1 iodine solid molecule, 2 HI gaseous molecules, 1 chlorine molecule. Let's see. This constant happens to be 1/1000th. So this is small and or this is big. At this particular temperature, I have very little of this and a whole bunch of this. Oh yeah, by the way, do you remember what's special about pure solids and pure liquids? As long as there is some pure solid or pure liquid there, it's not written in the equilibrium constant expression. Maybe because one reason you think of it as solids and liquids really don't have a definition of molarity. I suppose you could define the definition of a liquid in molarity, but we just don't. In some sense, the fact that this is there is tied up in that number. That's not a rigorous definition, but trust me, it's true. That's the rule. So if this is 1, if this were 1 and this were 1, that would be 1, and this would be it wouldn't be 1,000, it'd be the square root of 1,000. There we go. I wrote it out down here. this were 1 and this were 1, then this would be 31.6, because 31.6 squared is very close to 1,000. Another example. What if this was 0.01 and this was 2? What would this have to be? The answer is I don't know. But I do know that the math must all come out to be 0.001. So this one squared divided by this one squared, let's see, this one squared divided by this one squared, divide that into this one, and you should get 40. So we can play this game with any concentrations you like, as long as you know the constant should remain the same. Then, yeah, if we know this one and we know this one, then we can find this one. Or if we knew this one and this one, we can find this one. If we know this one and this one, we can find this one, as long as we know the constant. Or if you don't know the constant, then you really have to find the equilibrium concentrations or some representative equilibrium concentrations for the reactants and products. Well, I hope that didn't confuse you too much, but feel free to ask and practice and get better. Thanks, guys. See you in class.